Hello and welcome to the first part of our 27th lecture in our Calculus 3 course, Math 353. This is a lecture intended to be viewed on Tuesday, April the 14th. So today we are going to begin our discussion of spherical coordinates. We are likely to give this coordinate system a couple of lectures because it is, for a lot of folks, the trickiest to develop some intuition for of our coordinate systems for 3-space. But it is, as is always the case for these coordinate systems, going to make certain types of integrals much easier. If we can get a handle on what types of regions are best represented in spherical, then integrals over such regions will be much simpler when approached in spherical coordinates as opposed to attempting the integral via a less natural coordinate system. So we'll get to that, and we'll, by the end of the day, I think, be considering different regions and how to express them in spherical. But for the moment, let us think about the variables which make up the expression of a point in spherical coordinates and how to interpret these different variables. So spherical coordinates is chapter 15.8 in Stewart. If you would like further reference, please have a look at that. Stewart is a good book. But spherical, in Cartesian, 3-space is described by the variables x, y, z. We saw in cylindrical, the 3-space can be described by variables r, theta, and z, or r theta y, or r theta x for our three versions of cylindrical. In spherical, we are going to express points in 3-space in terms of the variables rho, theta, and phi here, all three of them being Greek letters this time around. So we'll look at each of these in turn. We'll begin with rho. Rho looks like a fancy P. It's kind of a P with a less straight back to it, and it is pronounced as R-H-O, rho. This is a lowercase rho. Rho is a kind of radius. In particular, it's the distance between the point in question and the origin. But do note that rho in spherical is different from our r in cylindrical. Rho is going to be the radius of a sphere in 3-space, where r was the radius of a circle in the xy plane. So for instance, if I draw my x, y, z coordinate system here, and I draw a point, so here's our point of interest there, I can draw the line segment from the origin of 3-space to that point. The length of that line segment is rho. So rho is the distance between the origin and the point in question. If I want to think about r in the same picture here, I would need to project my point straight down into the xy plane, and then I can draw a line segment from the origin to that projected point in the xy plane. The length of that line segment, which lies in the xy plane, is r, our radius from cylindrical coordinates. And in fact, the length of this leg, which represents my projection from my point in 3-space down to the closest point to it in the xy plane, the length of that line is actually z, our vertical rectangular coordinate from cylindrical coordinate system. So looking at this right angle that we've got here, going here, this right triangle, Pythagoras' theorem is going to tell me if I sum the squares of these two legs, I'll get the square of the hypotenuse, that hypotenuse being rho. So rho squared is actually r squared plus z squared here by Pythagoras' theorem. And we already knew in cylindrical that r squared can be written as x squared plus y squared, so I can make that substitution here and write rho squared as x squared plus y squared plus z squared. And that's going to be a formula that will be important to us, in particular later when we start thinking about translating between rectangular and spherical, back and forth, and also later still when we start turning integrals given in Cartesian into an equivalent integral represented in spherical. We might have x squared plus y squared plus z squared expressions in our integrand or in our limits of integration, turning into simple rho squared expressions. A consequence of this, well, sort of. I suppose more a consequence of just the geometry, the fact that rho is a length of a line segment here, is that rho is always going to be greater than or equal to 0, just like r was. We do not conceive of negative radii in this course. So that's rho, and this is an appropriate picture to get a handle of what rho represents. What about theta? So theta is actually the same theta that we had in cylindrical, and as we said there, it's the same theta that we talked about in polar coordinates when we were thinking about double integrals in the plane. So theta, we're using the same symbol because it is it has the same character in these three situations. In polar coordinates and cylindrical coordinates and spherical coordinates, theta is always an angle in the xy plane which begins with the positive x-axis and moves counterclockwise around until you reach the point in question. Here there's one extra step. We do have to go from the point in 3 space to its projection in the xy plane here, and then that gives us the line segment that we can go from the positive x-axis to find our angle theta. So it is still, in some sense, the angle in the xy plane from the x-axis to the point in question. It's just that the point in question may actually lie above or below the xy axis, and so you can consider the projection of that point into the xy axis first. As we said for polar and as we said for cylindrical, we will take theta to be between 0 and 2 pi usually. We will bend that rule if it serves our purposes. If we want to go from the negative y-axis over to the positive y-axis, we might call that theta going from negative pi over 2 to pi over 2, for instance. But typically, just as a first approximation here, you can think about theta going from 0 to 2 pi. Now, phi is new to us. Phi is going to be the most novel of these three variables. Rho had an analog in r, theta is just theta. Phi is going to be different. So phi is the angle between the positive z-axis and the line segment that runs from our point to the origin. So let's jump straight into the picture here. If I've got this point that I'm interested in 3 space, I can draw a line segment from the origin to that point, and I can create an angle from the positive z-axis down to that line segment. So phi, that's going to be angle phi. You start with a vertical line segment, and you drop it away from that vertical position until you achieve the appropriate angle for the point that you're interested in. So starting with a pencil that's standing straight up, you could let that pencil start to fall and stop it as soon as it points at the point that you're interested in. And the angle through which the pencil has fallen is your phi. So this is in some sense a vertical angle. It tells you how much things have moved sort of in the vertical direction, but not as a straight vertical like our delta z was, rather this angular vertical movement in terms of delta phi, given in terms of delta phi. So we will always take phi to be between 0 and pi. This is not a rule that we bend. If I wanted to sort of come over here to the other side of the positive z-axis, that's not a negative phi. That's the same value as phi, but then with theta having rotated around to get to the backside over there. So phi moving from 0 to some positive value actually takes you through changes in phi for all different values of theta, meaning you get all the different orientations. I can take this line segment and rotate it around the z-axis as theta goes from 0 to 2 pi, and I'll get a half cone that every point on which is given by the same value for phi here. We'll return to this idea when we consider the grid surfaces for spherical coordinates, but hopefully that makes sense. Here I'm looking at a phi value that's dropping to some point in the xy plane where the x and y values are both positive. So this projection point here is in the first quadrant of the xy plane. If I was to just mirror it straight across the z-axis, we would get a point over here in the third quadrant of the xy plane. That point would have the same value for phi, just with theta having rotated through pi degrees or 180 degrees there. Alright, again, we'll return to that when we think about the grid surfaces, but we do take phi to be between 0 and pi, and that's not a rule that we bend. And you can think about the fact that phi equal to 0 gives you the positive z-axis. Phi equal to pi over 2 is going to give us the xy plane. So that's where phi has gone from vertical down through an angle of 90 degrees to lie exactly on the xy plane. And we can get the whole xy plane by taking any value for theta and any value for rho to give us our distance from the origin. So phi equal to pi over 2 gives us the xy plane. Phi equal to pi will continue to rotate down until phi equal to pi gives us the negative z-axis here. I'll give that some thought. Make sure that that all sits well with you. So to summarize the way that these different values of rho, theta, and phi can give us all the points in 3 space, if we fix rho to begin with, and we let phi rotate from 0 to pi, that's going to trace out this half circle here with theta equal to 0. It'll be a half circle in the xz plane that intersects the x-axis here when phi is pi over 2, and then hits the negative z-axis when phi is pi. So we're tracing out this vertical half circle that lies in the xz plane as phi goes from 0 to pi. Now we'll let theta go from 0 to 2 pi, and this half circle is actually going to rotate around the z-axis, as indicated here, to give me the sphere of radius rho centered at the origin. So I had a half circle over here on the right-hand side, and I let that rotate as theta went from 0 to 2 pi. I let that half circle rotate around the z-axis, and it traced out now a sphere, the whole shell given here. And now I can do that for any rho values. If I take rho to be smaller, I'll get concentric spheres inside this one, and if I take rho to be larger, I'll get concentric spheres outside this one. So letting phi and theta go through their values for a fixed rho gives you a sphere at the origin. Do that for any value of rho, and you can get all the spheres centered at the origin, and every point in 3 space lies on some sphere centered at the origin. So taking these values for rho, theta, and phi will allow us to describe any point in 3 space, as it should. If it's a good coordinate system, it should give an address to every point in 3 space, and this does. So as we have done for other coordinate systems, we're going to think about what does a quote-unquote rectangular box look like in this coordinate system, and what do the grid surfaces look like in this coordinate system. We thought about rectangles and grid lines in 2 space, and rectangular boxes and grid surfaces in 3 space. We do this, as always, to get some sense of which types of regions will be naturally represented in this new coordinate system, spherical now. So I'm going to throw problems at you ultimately and not tell you how to integrate it. I'm just going to say integrate this function over this region. You're going to have to look at the region and decide which coordinate system will serve best to represent that region. And so we want to develop some intuition for which types of regions are well represented in spherical coordinates. And this is to that end. So in spherical, a rectangular box is going to be a collection of points of this form. We're going to take all the rho, theta, phi values such that rho is bounded between constants a and b, theta is bounded between constants alpha and beta, and phi is bounded between constants gamma and delta. These are the lowercase Greek letters gamma and delta. If you don't want to mess with Greek letters, you can use C and D and E and F here, that's fine. So, as always, rectangular boxes just represent a region where each of the variables involved has constant bounds. And what does that look like here? It's going to look like a region of this type. So down here on the bottom, depending on which way you perceive this flippable orientation, but here the region I'm tracing out now, I perceive to be the bottom of this currently. And so that looks like a rectangle in polar. Just like when we did cylindrical, we started with a rectangle in polar, but then we projected it up through a straight delta z increment in the positive direction. Here we're not doing that. Instead, we've got a curved vertical angle increment for our delta phi expression. So this is like our delta rho, a change in the radius. This is something like delta theta. It's actually going to depend on your distance from the origin, just as it did in cylindrical. And this is something like our delta phi region. This is again going to depend on the distance from the origin, as well as some other factors in this case. So I have some approximately symbols in here, because we're going to revisit this image when we think about what our dv term looks like in spherical. But the gist of it here, for our purposes here, we're looking at the change in the radius, a change in our angle theta, and a change in our angle phi. So it looks similar to a rectangular box in cylindrical, but we have these curved edges here in the vertical direction, as well as in the horizontal direction here. So it's not my best work in terms of drawings. I do encourage you to have a look at page 1087 in Stewart. Stewart is full of lovely drawings. So please do look over, especially if you're having any difficulties with the spherical stuff, and that's totally normal. It is not at all unheard of for some of the best students in the class to have trouble getting a handle on spherical coordinates initially. I definitely recommend that you take a look at the pictures and some of the examples in Stewart. Stewart is a much better artist than I am, or whoever creates the graphical images in Stewart. Whoever did the graphical design in Stewart is a better artist than I am, so please look at the pictures. Pictures are helpful. Let's think about grid surfaces, our counterpoint to rectangular boxes. So we're going to take each of these variables and set them equal to a constant and see what type of region that represents in 3 space. And that will again give us some sense of how spherical divides up 3 space, thereby giving us some sense of which types of regions are best represented in spherical coordinates. So if we set rho equal to a constant, you are just going to get spheres centered at the origin. If I take rho to be 2, for instance, I'm saying I want all points that are a distance 2 from the origin, and that is going to be the sphere of radius 2 centered at the origin. So I've done my best to draw a sphere here centered at the origin. If we take theta equal to a constant, we're going to get half planes with the z-axis as its edge, as their edges, and having rotated through an angle theta in the xy plane, just like we saw in cylindrical. So it's the exact same theta that it was in cylindrical, and we get the exact same type of geometric region if you set theta equal to a constant. So I've done my best to represent this here. This line is the line in the xy plane that's represented by theta equal to this constant value, and I take all points above and below that line for the collection of objects represented by theta equal to a constant in spherical coordinates. We could let phi rotate from 0 to pi to trace out the half circle in this plane, and then represent that half circle of any radius to get a bunch of concentric half circles, which would give me the whole of this half plane. Lastly, we will set phi equal to a constant. When phi is set equal to a constant, that's going to give you half of a right cone having the origin as its vertex. So here's an angle phi. I've dropped from the positive z-axis down through this angle phi to this line segment, and I can take that and rotate it through all the values of theta, maintaining my same angular distance from the positive z-axis, and I will get the upper half of the right cone with the origin as its vertex here. If phi, so for in this picture, phi is strictly between 0 and pi over 2, were phi between pi over 2 and pi, we would get the lower half of such a cone. So we would have rotated through an angle greater than pi over 2, we would be down in the below the xy plane, and then rotate theta from 0 to 2 pi to get the lower half of such a cone. And again, I've done my best with the drawings, but Stewart does it better. So on page 1085 of Stewart, figures 2, 3, and 4 will show you these grid surfaces for spherical coordinates. So, next obvious question is if you can represent any point in 3 space either via rectangular or via spherical, the same point has a representation in rectangular and a representation in spherical. How do we translate back and forth between those different representations? So we have already seen an equation just based on the geometry and Pythagoras' theorem that rho squared should be x squared plus y squared plus z squared. That means that if somebody hands us an xyz triple, we can find the associated value rho. Just take the square root of the above equation and you'll get rho. So we know how to find rho given x, y, and z. What if instead we are given rho, theta, and phi, and we want to find x or y or z? So let me also say, I guess here, for if you're given x, y, and z, there are ways to find theta, and there are ways to find phi as well. As was the case for cylindrical coordinates, those equations in practice aren't as useful. So being able to find this variable in spherical, given a full expression of the point in Cartesian, that's more practical, and that's the one that we'll focus on. There are multiple equations for finding theta, given x, y, and z, and there are multiple equations for finding phi, given x, y, and z, but we're not going to concern ourselves with that. We are, however, going to think about if we're given a point in spherical, how do we find the z, how do we find the y, and how do we find the x values? So we're going to start with the easy one, which is z here, and we'll also think about finding x and y momentarily. So given a rho, theta, phi triple, That's an expression of the point, of some point in spherical coordinates. How do you find the z value? So geometry is your friend here. Drawing pictures is the way to go. So here's the point that we have been handed. Here's the rho value associated. Here is the phi value dropping from the positive z-axis down to that line segment. You'll also note that this is the same phi here. There's an old school theorem in geometry that says if you have one line and it bisects two parallel lines, then the complementary angles, maybe that's not what it's called, the interior angles formed by this bisecting line are the same. Something of that nature. It should be believable to you based on the geometry to see this picture. If I let this angle over here close up, then this vertical line is going to pull over to the left, and you'll see this angle closing up as well. So they move together when they're both 90, or when one's 90, the other has to be 90, and so forth. So hopefully that's clear, that this is also phi, and theta is this angle in the xy plane moving from the positive x-axis counterclockwise. So here's the rho that we've been given, here's the phi that we've been given, and here's the theta that we've been given. The length of this vertical leg is our z value that we're going to look for. So I'm actually going to take this triangle and I'm going to cut it out of the three-dimensional picture so I can write it down flat and think about it in two space and simplify my consideration here. There's a lot of this in these types of problems when you're going from spherical to Cartesian here. You want to draw the full picture first to figure out what's going on, but then you may realize that you only want to take a portion of that picture to focus on and to simplify your drawing. So I've taken this triangle here and I've snipped it out of the larger picture and I'm considering it in isolation over here. So here's my z value. This was the vertical leg here. I've taken the triangle and I've laid it over on its side. So my z leg was the vertical leg here. It's the horizontal leg here. This is rho, my hypotenuse, and my angle phi here, interior, ends up over here in the right-hand corner. So I can say right away at this point that cosine of phi is z over rho. Cosine is adjacent over hypotenuse. So cosine of phi is going to be z over rho, and it's a simple matter to solve that for z. Z is then going to be rho cosine of z. So that's how you find z given, oh drat, rho cosine of phi. That's a phi right there. I will change this in the notes that I post, but I do not have time to re-record this video, so please make note that this should be z equals rho cosine of phi. It will be written correctly in other portions of the slides here. So, now to find x and y, we're going to draw similar pictures, and we're going to have to think about what's going on there. So, here's exactly the same picture I drew a moment ago, except instead of labeling the vertical leg as z, I'm now labeling this horizontal leg as r. So I'm going to take that triangle, I'm going to snip it out, I'm going to draw it over here, and now I can say that sine of phi is opposite over hypotenuse, which is going to be r over rho. Sine of phi is r over rho, that means r is going to be rho sine phi. So the first thing I'm doing is figuring out how long is this leg, which represents the projection of the point that I'm interested in up here, down into the xy plane. So the first thing I'm doing is I'm dropping down to the xy plane and I'm finding my r value. Now with r and theta in hand, I'll be able to figure out what my x value is, rather my x value here, and also my y value. So with this expression for r in hand, we're now going to focus on the xy plane, and in the xy plane the picture looks like this. Here's our r value that we just found, here's the theta that was given to us, and here's x, and here's y. So cosine of theta is going to be x over r, which means that x will be r cosine theta, and our expression for r was that r equaled rho sine of phi. That means that x will be rho sine of phi cosine theta, and likewise y is going to be rho sine of phi sine of theta. That's coming from sine of theta being y over r, solving for y, and substituting the expression that we just found for r. So here's the proper expression for z, as I promised. Apologies for that. But what we have just found is that x is going to be rho sine phi cosine theta, y will be rho sine phi sine theta, and z is going to be rho cosine of phi. So these are not the most elegant equations that we have seen. There's a fair bit going on, and there's multiple pieces to them, so that's annoying. You obviously have references while you're taking exams now, but I do want us to think about the intuition behind these a bit. So you're starting with a point that's a distance rho from the origin. When we take sine of phi and multiply that by rho, that's projecting us down into the xy plane. If you remember, rho sine of phi was our r. So by taking my rho value and multiplying it by sine of phi, I'm projecting into the xy plane. Taking that and multiplying it by cosine theta further projects me onto the x-axis. Likewise, for my y values, I start with rho sine of phi, I've projected into the xy plane, and now I multiply by sine of theta to project over onto the y-axis. So cosine of theta to get to the x-axis, sine of theta to get to the y-axis. If I'm getting to the z-axis, I never project into the xy plane using sine of phi. Instead, I use cosine of phi to project over onto the z-axis directly. So sine versus cosine of phi projects onto the xy plane, or the z-axis respectively, and if you have projected into the xy plane, cosine of theta versus sine of theta will project you onto the x and y axes, respectively. So that's the idea behind these equations. They are somewhat intelligible, interpretable. I do not do well memorizing them, but with a quick sketch I can remind myself of the form of them if needs be. So summarizing these translational equations, moving back and forth between rectangular and spherical, we have rho squared equal to x squared plus y squared plus z squared. We have x equal to rho sine phi cosine theta, and we have r equal to rho sine phi sine theta. And finally, z is rho cosine of phi. So let's give you folks a sample problem. We will wrap up this part of this lecture with this sample problem. We'll actually have another sample problem at the beginning of our next part 2 of this lecture, but we'll cut this here just for the sake of the size of the file. So sample problem: if rho, theta, and phi are given by 2 pi over 2 and pi over 2. So somebody hands you a triple, 2 pi over 2 pi over 2, and that is a point described in spherical coordinates. Then find the equivalent expression for this point in Cartesian coordinates. So find for me the x, the y, and the z value associated with whatever point this is that's handed to you in spherical. There's 2 ways to do this. You can do it the more analytic way using the formulas that we have, and that's good. It's also worth thinking about trying to break this down geometrically. So think about what these different values for these different variables mean, and see if you can maybe tease out the location of the point using some geometric intuition. To give that some thought, we will reconvene in just a moment here and have a look at 2 different solutions to this problem. Alright, so first of all, we're going to do this sort of the easy way in some sense. Well, the obvious way, let's say. We're just going to use the formulas that we've developed. So x is rho sine phi cosine theta. That's going to be 2 sine of pi over 2 cosine of pi over 2. Knowing what my trig functions are at these points, I can write that as 2 times 1 times 0, which is 0. Y is rho sine phi sine theta. That's giving me 2 times 1, which is just 2. And z is rho cosine phi. That'll give me 2 cosine of pi over 2, which is 2 times 0, which is 0. So in rectangular coordinates, this point is 0, 2, 0. In spherical, it was 2 pi over 2 pi over 2. In Cartesian, it's 0, 2, 0. The other way that one could do this problem, using some geometric reasoning, is to realize that our phi value being pi over 2 means we're looking at a point in the xy plane. So my angle phi from the positive z-axis has dropped from the positive z-axis through an angle of pi over 2 to land exactly on the xy plane. So I know that I've got a z equal to 0 in my Cartesian representation. Since we're looking at the xy plane here, that means z would have to be 0. Then I see a theta value of pi over 2 as well. Theta at pi over 2 means I started on the positive z-axis and rotated counterclockwise through 90 degrees, landing me exactly on the positive y-axis. So now I know that x is going to be 0 because I am lying at a point, or I'm looking at a point that lies on the positive y-axis. And finally, knowing that my point is a distance 2 from the origin, means that the y component has to be 2. This is a point that lies on the positive y-axis and is a distance 2 from the origin. So I can see that it's going to be 0 to 0. It has to be that point now. And here it is. We knew that it dropped from the positive z-axis down to the xy plane, and also that we had rotated over till we lied on the positive y-axis here. And since it's a distance 2 from the origin, 2 is just its y component. Its x component being 0, and its z component being 0. Alright, that'll do it for the first part of our lecture. For the second part, we will look at another example, another sample problem similar to this. We will also start thinking about how to represent different regions in spherical coordinates. So I might throw a region at you, ask for its representation in spherical, or I might give you some bounds for the 3 variables in spherical and ask you what type of region or what that region looks like. And then finally, we will consider how to integrate in spherical coordinates. So what does our dv expression look like, and how do we set up triple integrals in spherical? Most of next lecture will be examples and sample problems of performing such integrals in spherical coordinates. I thank you. I will speak with you again momentarily.